Hello everyone, today we're presenting to you our paper Risk-Sensitive Rendezvous Algorithm for Heterogeneous Agents in Numbered Environments. This research was made possible by the NSF National Bodies Initiative. First, let me introduce the framework behind this paper. In simple words, it envisions having ride-sharing vehicles to do the heavy lifting in urban areas. This only applies to the last mile problem, which is the last leg before delivering the package to the customer. The way it works is that UASs drop and pick up packages from ride-sharing vehicles. This way, the majority of the distance between the customer and the closest depot is covered by ground vehicles. Clearly, the main driver is the extra range afforded by having cars carrying the package around. Because we theoretically need less delivery trucks, we can expect to reduce traffic for everyone else. And coincidentally, because we fly for some portion of the mission, the UAS avoids traffic altogether and improves delivery times. Partially automating the service also brings us reliability and other common attributes of autonomy. So what are some of the open problems we are solving in this framework? One is, for example, on the controller design for doing the actual landing maneuver. It's a complex problem for many reasons, which has also been studied by other groups. Another problem is the robust flight controllers to make sure that we don't crash into anyone or anything due to hardware failures or environmental factors such as wind. Another research vector is finding the customer and sharing information between neighboring drones to navigate efficiently in dense urban environments. We also want to perform this delivery in a socially aware fashion so that humans going about their lives don't feel threatened by flying robots. Another hard problem is the challenge of distributing facilities and drones optimally to make sure that we use the network to the best of its ability. The problem we are discussing today is the one that deals with the rendezvous with the car, that is, planning the point on the road where we are going to attempt the landing maneuver and do so safely. So let's introduce that problem. At first, it seems like a solved problem, not very interesting, but when implementing a naive version of it just to complement the landing maneuver, I immediately ran into several theoretical barriers that needed special attention. Looking at this figure here, the blue ball will be the maximum range of the drone with no payload, so that the drone can go up to the border and back with one battery. This is useless for us because we're carrying a payload. The green ball is the same thing but carrying a payload the entire time. This is more realistic, but when we sacrifice a huge amount of range for no reason, because on the way back, there is no payload. So we want to work on the red ball. That is the ball where if you fly up to the border, drop the package and head back, you finish with no battery. Let's piece an example car and road here. At this moment in time, the car is really far away, but you're planning on where to fly to and meet that car. Because of uncertainties, the estimation is stochastic. Because the road passes through the mixed range region, a rendezvous is possible. If we fail to drop the package off, we will crash. Failure is both spatial and temporal, and hovering at a location waiting for the car to drive by is suboptimal. And because this plan is in the order of multiple minutes, any projection that we make is highly volatile. With these assumptions, this is not a solved problem. And the reason why is because these problems usually fall into two categories, and neither really works for our use case on its own. The first category is the one where we have full knowledge of the problem, or assume some small non-critical uncertainties. If we're thinking of the UAS as the hunter and the car as the prey, for example, this amounts to knowing exactly where the driver would be at any given time. The solution then is a relatively easy auto-control problem. One example would be landing on a carrier. The carrier tells the pilot exactly what they're doing so that the pilot can craft his or her plan accordingly. The other end of the spectrum is when you don't know what the prey is doing. And there are many tools that guarantee a rendezvous in finite time given some conditions, but the problem is that we don't have any way of planning battery expenditure and timing of rendezvous. With that in time, it's pretty obvious that we need to craft a new set of tools that sits in between. It accepts uncertainties where they exist and provides guarantees where we need them. We will need tools that satisfy constraints, tools that can deal with uncertain driver behavior, with multiple paths, and that can plan a return route. On top of it all, we need tools that can run on an embedded computer. This last bullet point is important because we can always rely on huge amount of data, but if we can simplify the algorithm to run on existing SoCs, the cost and scalability of implementation is much better. This is what it looks like for a single agent, single path. That means that there is one driver, one UAS, and one path to worry about. The goal is simple. The drone departs from some location far from the path and needs to meet the driver at some future point in time and fly back to the landing location. The challenge is that we have limited battery, and the driver behavior is uncertain. Our goal then, as a planner, is to create a delivery path which has a high probability of success and one abort path that doesn't depend on the driver and has a guaranteed chance of success. It boils down to solving three separate problems. One is learning driver behavior. Two is dealing with long time horizons by intelligently using the learned model. And three is crafting an optimization problem that minimizes risk. First, the learning problem. As I said, the driver behavior is uncertain. Driver could be going faster, slower, can be just erratic. We don't really know when the mission starts. One way of checking driver behavior is to learn the position function, that is, theta sub d, but that is overly ambitious because we're dealing with multiple minutes here, and uncertainty propagation will make any plan too risky. Instead, we do two things. We assume that we know the velocity profile of the driver, which is a very weak assumption because this data is very easy to collect, and we also assume that we can measure the driver position and velocity with added Gaussian noise. These two things, instead of learning driver position, we learn driver velocity as a function of historical velocity. That is, given that the average driver cruises at 60 miles per hour, for example, how fast or slow do we expect our driver to be cruising along the same stretch of road? There are two ways going about this. The simplest one, and the one that we use in this paper, is using Bayesian linear regression, as shown in this slide. If we do this, we can integrate the basis functions and just plug in weights to get mean and variance functions. These functions are well behaved, so we just feed them into the optimization problem. Next is that optimization problem. Here, we build an MPC-like setup, but not traditional at all. The sample horizon is fixed, that is, the number of samples is always fixed. But unlike MPC, the time horizon is not fixed. Our control inputs are not only velocity, but time as well. So the solver can choose when to rendezvous and when to land. We assume sequence integrated dynamics, and we think that that's okay because the scale of these missions is so large that in the grand scheme of things, we can make any controllable robot follow a straight line. Battery dynamics are free to have any differentiable form, and you can see the optimal control problem on the right, where we notice there's a minimization of time, a minimization of some quantity, and a maximization of t sub 1, which is time. This will become clear in the next slide. The goal is twofold. Wait as much as you can for more data, but not too long that your abort path is no longer feasible. So that's what we designed for. We minimize time spent at each segment, but maximize time spent in segment 1. That sits between the drone and the point of no return. This point of no return is a point that, when reached, necessitates a decision. At PNR, the drone needs to choose between aborting or delivering, and we hope that the extra time afforded until that happens is enough to justify a delivery decision due to the amount of data collected. The other element is a cost function, rho sub r. This is a risk measure, and I'll talk about risk measures soon, but for now think of it as an undesirable quantity that we want to minimize. Other constraints are spatial, so that the rendezvous points are on the road, for example, or temporal to make sure that we don't spend too much time or too little time in a segment, and also energetic, so that our plan doesn't exceed the resources we have available. Now I'll introduce downside risk, which is the family of risk measures that we're using. So this picture on the right is well known. Say you have some cost or state-related constraint. You can use stochastic MPC to bring the mean below the constraint, or also minimize variance for an in-between solution. I'd say, however, that the best solution here, safety-wise, would be this. A downside risk measure wouldn't try to minimize all the variance, instead just the variance that is unsafe, effectively shifting the variance down. Now, in dynamic systems, you can rarely do this for several reasons. But even if you can't simply shift it, a DSR criterion in optimal control will still find solutions that are generally better safety-wise than simple mean variance. One popular example is CVAR, which minimizes the undesirable tails of distributions. Luckily for us, in our setting, we can do this minimization. So how do we use downside risk in this setup? We do so geometrically. The idea is simple. We sample the confidence bound at some chosen threshold and compute how much extra energy will be necessary if that outcome was to happen. Then we say that the downside potential, that is the potential loss associated with the downside risk, is, and we want to be meeting some threshold. In this case, it's energy. So we see that the downside potential is below some number. We have enough battery to complete that mission. Otherwise, that is a possibly bad plan and we don't go with it. So here's an overview. We have three main modules, all depend on each other. We learn their behavior in a way that makes it easier for us to get these risk measures. We feed that to an NPC-like controller, and then finally we check risk bounds before committing to anything. Here's a low-risk result, or the decisions to proceed with the rendezvous. You consider the downside potential is below a set threshold when we reach PNR. So that means that we're good to go, and we continue with the rendezvous. Also note that the algorithm is constantly maximizing the plan's energy so that we fully utilize the available range. Note that the choice of threshold is also entirely up to the designer and the characteristics of the UAS. In this next scenario, everything is the same mission, but I raised the noise in the sensors and also made the driver more erratic. So it's hard to predict, given a speed limit, for example, what is the speed of that particular driver. What happens is that at decision time, the downside potential is too high and the UAV has to abort. Thank you for listening to this video. I hope to answer questions. I'd like to thank UIUC, University of Illinois, and also NSF for funding this research. Thank you.